Hi again, everybody. We're going to talk about metallic bonding. All right, so metallic bonding works on the idea that metals easily give up those electrons, especially those transition metals, because they'll give them up not just from the outside, but from those inner D and F shells. So when one or more metals bonds together, these electrons move away from that center positive metal cation, and they create kind of like a C. So the electrons are moving freely between all these cations, and the cations basically are just floating in a sea of negative charge. Okay. Um, and the fact that the electrons are easily able to move around, and then the cations are easily able to move around, explains most of metal properties. Mm. All right, so the attraction of the positive cations for the negative electrons is what holds this particular bond together. Okay, so for ionic, it's the electrostatic attraction between positive and negative ions. In the metallic bonding, it's the positive centers of the metal atoms for those delocalized electrons, that attraction. It's still electrostatic in nature, but it's not as rigid because, again, those electrons freely move. And the ability for the electrons to move freely between cations is why metals are conductive, because those electrons move and they transmit that charge. So the properties of metal are that they're very durable, they're ductile, they're malleable, they have low melting points, high boiling points, they're conductive in every state, and the hardness of a metal actually increases with the number of delocalized electrons it has. Now, if you don't know, ductile means that you can pull something into a wire. So think copper wiring in your house. And malleable is sheets. So think aluminum foil. And we're going to see an example of this. Okay. So of course, coils of wire are an example of something being ductile, and the rolls of foil, like your tin foil that you use at home, those are examples of a metal being malleable because we actually press those between two really heavy rollers, and it makes it come out as a sheet. Now, if you look really closely at these melting and boiling points, you can see it on the group 1 chart really easy, but the red bars are the melting points, and you can see they're really low. The blue bars are the boiling points, and they're anywhere between 600 and 1500 degrees Celsius, just for the group 1 elements that have very few electrons to give up. And if you look at group 2, those melting and boiling points have a little bit of a different ratio. So if you look at the melting points, right, the highest melting point is that beryllium, and that's at what, 12, a little over 1200, right? But if you look at its boiling point, it's somewhere between 2000 and 3000. Okay, so the reason for the difference between the melting and boiling points is that if a metal is melted, those electrons can still move freely between those already energized cations. But if you boil a metal, then you are forcing those electrons to go back to their original state of not being delocalized, because those gaseous metal atoms are moving too fast to support that delocalized state. Okay, but metals are still conductive as a gas because then the whole atom is moving freely, and so the whole atom is what conducts that electricity. Okay, but the breaking of that delocalized electron bond is why those boiling points are so high. All right, so really quick, we're going to look at alloys. Okay, so a pure metal has cations of only one element, right, on that delocalized electron C. So let's imagine that blue is whatever metal you want, okay? A substitutional alloy is when some of those cations are replaced by cations of another similarly sized element. So now we have some yellow circles in there, okay? Those yellow circles represent that new element. An interstitial alloy is when the original cations stay the same, but the spaces between those cations are filled with atoms of a smaller element. Okay, so that's the red dots. So a pure metal would be something like pure gold. A substitutional alloy would be like a copper gold alloy, which is common for most of your types of like 10 karat, 14 karat gold. They all have a little bit of silver and a little bit of copper. And those silver and copper molecules act as substitutional alloys. They replace some of the gold. Why do we do that? Because it makes it harder, but it still keeps that pretty gold color that everybody likes. Interstitial alloys are things like carbon steel. The blue molecules in that case would be the iron and the red would be the carbon because carbon is much smaller than iron. Instead of replacing it, it actually fills in those spaces. And what that does is it makes it more rigid because then those metal cations can't slide against each other like they would if they didn't have anything between them. So this makes it less malleable, less ductile, but stronger and harder. So this is why we use steel on things like support beams, but not in things where we have like a lot of shear because they can't slide. And so once it hits a certain point, it'll just completely shear and it'll break instead of bend. So you have to watch your ratios on those. All right, so that's pretty much it for metallic bonding. This is the easiest form of bonding out of the three. And if you need to go back and rewatch anything, feel free to do that. I'll see you guys in the next video.